Okay, chemistry 1411. Where we left off last class was somewhere around this area, somewhere around here. It might not have been exactly on this slide, but we talked about this question and this concept. So the concept, which was a factor that influences entropy. The first two were phase of matter. The second one was temperature. And then we talked about the type and number of particles that make up a substance. And what I didn't originally have on my slide, but what I want to address, I copied this straight out of our textbook, and I'll read it to you quickly. It just says, heavier atoms possess greater entropy at a given temperature than lighter atoms. For molecules, the greater number of atoms increase the number of ways in which the molecules can vibrate, and thus the number of possible microstates, and of course the entropy is going to increase. And so based on that concept, we answered question 12, and we answered parts A and C. So for these molecules, and of course helium is an atom, but we looked at these examples in the last class, and we arranged them in order of increasing entropy, and we said that the entropy increases as mass and complexity of the molecules increases. So what I added to this, since last class was this question right here, this is a Mr. Dion question. If we wanted to arrange these three noble gases, neon, argon, and helium, in terms of their increasing entropy, could anybody tell me which one of these noble gases, which one of these elements would have the least entropy or the lowest entropy based on that statement at the top of this slide? And it's not a trick. Yeah, absolutely. It's helium. Yeah, helium is the lightest, right? And we said that heavier atoms possess a greater entropy. So the lightest atom should possess the least entropy. Yes, so it would be helium, gas, and then the next one would be what? Would be neon, because neon comes after helium, and then argon is the heaviest of all three. And so it would have the greatest entropy. And again, it's based on the mass. So mass of atoms is the rationale there. That's all there is to it. All right. Then we discussed a pure substance compared to a mixture, and we discussed how a mixture has an increase in entropy, and then we solved this problem too. So this is a new slide, and I just want to kind of go over a qualitative approach to evaluating entropy changes in a reaction, because sometimes we can take just a qualitative look. We can just look at what's happening in a reaction, and we can predict what is happening in terms of our change in entropy in the reaction. So it says that an entropy change is always going to be dictated by the substances in the reaction with the most entropy. And we know that entropy increases as you go from a solid to a liquid to a gas, but an aqueous solution is going to be somewhere in between a pure liquid and a gas, right? It should have a higher entropy than a pure liquid because it's a mixture of two or more components, but it's not going to have the entropy of a gas because the particles are not going to be separated as much. So here's how we do that qualitative approach right here. It says, when gases are formed, produced, or consumed in a chemical reaction, if your reaction ends up making more gas molecules than it consumes, you've got an increase in entropy. The opposite is also true. If the total number of gas molecules in a reaction decreases, right, we know that gases have the greatest entropy. Okay, if the total number of gas molecules diminishes or decreases, our entropy is decreasing. Now, the last one is this. This is kind of an interesting one, and I need you to remember this, is that if there's no net change in the total number of gas molecules, the delta S, it might be positive, it might be negative. So you might have an increase or a decrease in entropy, but the point is this, it's going to be small. Okay, it's going to be a small change in entropy. Now, keep in mind, this works when we're dealing with gases, okay, when gases are produced or consumed. So based on this concept, I want to take a look at some problems. Now, this is, again, based off of the concepts that were covered on the last slide. So it just says, predict whether the entropy change of the system in each of the following reactions is positive or negative. So the first reaction, A, we combine 2 molecules of gaseous hydrogen plus 1 molecule of gaseous oxygen, and we end up with 2 molecules of water in the liquid phase. What do you think is happening here? Is this an increase in entropy, a decrease, or no change, or very small change? Based off of what was said in the last slide. Yes, it's going to be negative, right? So this is going to be a negative delta S, or delta S is going to be less than 0, right? Because we're going from two gases, 3 molecules of gas or 3 moles of gas, however you want to look at it, that have a lot of mobility, a lot of freedom, a lot of different particles, and then we're making a liquid, and there's only one type of particle, okay? The next one, we move down to B, we're taking ammonium chloride, which is a solid at room temperature, and then we're causing that to undergo a sublimation from the solid to the gaseous phase, but it's being separated into ammonia gas and hydrogen chloride gas. What do you think is happening here? Is this positive, negative, or no change? Yeah, increases, positive, whatever you want to call it. So I'd say here this is a positive change in delta S. So delta S is going to be greater than 0, right? Look, we're going from a solid to having 2 particles of gas. So of course that's going to be an increase in disorder. And I'll just do the last one for you quickly. Oops, the last one, we're taking hydrogen plus, if we think about it, moles, 1 mole of hydrogen plus 1 mole of bromine, both in the gaseous phase, and we end up with 2 moles of HBr. Well, there's going to be virtually no change here. Okay, it's going to be small because here we have 2 moles of gas over here, and then we still have 2 moles of gas here. And so we'll just put, for this one, we'll put a small change. Small change in delta S, could be positive or negative. We're not sure. Okay, there you go. That's just something that I didn't go over with you in the last class, and I thought about it since then, and I thought, this is something that we should take a look at. But you know what? If you understood those 4 factors that affect entropy, I bet you were able to figure this out very quickly with me, okay? Usually my students are pretty good at predicting increases and decreases, or increases and decreases in entropy of reactions or a system. All right, well, let's get to it. This is where I wanted to get to today, which is section 16.3, which deals with the second and third laws of thermodynamics. So I'm going to rehash a little bit of what I talked about in the last class. I introduced the concept of the system, surroundings, and universe. So a system, you're going to hear me say the word system a lot in this chapter, especially in this section and the next section. A system really just means the part of the universe that's of specific interest to a chemist, and you're all chemistry students. We're talking about the reaction, right? A chemical reaction, that is our system. Now, surroundings is actually the entire rest of the universe. But again, as I told you last lecture, if you do a reaction in the lab, what's happening on the other side of the earth or the other side of the universe is not going to be affected by your reaction. And so the surroundings is actually just the immediate surroundings. So it's the environment that's immediately around the system. So we have the system shown here. We have a flask with a reaction inside of it. The surroundings is just the immediate surroundings or nearby that reaction. And so when we talk about the universe in chemistry class, we're not actually talking about, it's got nothing to do with, space or anything like that. We're not going to be talking about the planets and all that kind of thing. All we're talking about in the universe in chemistry is just the combined system and surroundings. Okay? So the system plus surroundings is the universe. And again, the universe is just the environment where the reaction is occurring and the environment around that reaction. Okay? So again, universe doesn't have anything to do with, stars and planets or anything like that. Just the immediate surroundings and the system itself. Okay, so now that we've established that, well, let's get into what the actual second law of thermodynamics is. First of all, we see that an entropy change in the universe is the sum of the entropy changes for the system and the surroundings. And so the second law of thermodynamics is based off of that statement. It says that when the entropy of the universe is increasing, we have a spontaneous process. Okay? I'm going to repeat that. It says the second law of thermodynamics is simply that all spontaneous reactions or changes cause an increase in the entropy of the universe. So when this delta S, when that is greater than 0, it is spontaneous. Okay? It's spontaneous when it's greater than 0. When it's less than 0, you have a non-spontaneous reaction. And when it's at 0, you know, when the delta S, when there's no change in the entropy of the universe, we've got a process that's at equilibrium. And these three concepts here are going to be important for you to know, okay? An increase in entropy of the universe, spontaneous reaction. Decrease in entropy of the universe, non-spontaneous reaction. And when there's no change in the entropy in the universe for our reaction, overall, the change in entropy plus the system and the surroundings, we have a process that's at equilibrium. Because these concepts are going to come up quite a few times in the remainder of this chapter. Well, let's talk about the system first. We'll talk about the system, and then we'll talk about the surroundings. So again, I told you that the system is simply our reaction, okay? The system is nothing more than a chemical reaction. So if we want to calculate the change in entropy of a system, okay, it's going to be the difference between the entropy of what we end up with, subtract the entropy of what we started with. Put another way, we say the change in entropy of our reaction is going to be the entropy of the products, subtract the entropy of the reactants. Again, that is how we calculate the difference in entropy over our reaction that occurs. And our reaction is the system, isn't it? Right? Over here, if you're like, these two equations are the same, Mr. Dion. Yeah, they are. The difference is, here we said system, here we said reaction. And again, in chemistry class, we're focused on reactions, aren't we? So when I talk about system, I'm talking about a reaction. And when I want to calculate the change in entropy of that reaction, I simply take the entropy of the products minus the entropy of the reactant. So you might be wondering, well, how do I measure the entropy of a product? How do I measure the entropy of a reactant? Well, you cannot measure that directly. However, it's change from, or the change in entropy from a reference point can be measured. What is that reference point? Well, in order for me to tell you what the reference point is, let me tell you what the third law of thermodynamics is. The third law of thermodynamics states that a perfect crystal, so with no impurities, has 0 entropy at a temperature of 0 Kelvin. Okay, a little bit more about absolute zero. It says 0 Kelvin is absolute zero. There's no temperature that's possible. There's no temperature lower than 0 Kelvin. At 0 Kelvin, there is no movement. Okay, the electrons aren't moving. Nothing is moving. There's no molecular movement at 0 Kelvin. And so if there's no molecular movement at 0 Kelvin, then how would you calculate the entropy of that system? Well, there's only one possible microstate, isn't there? Think about it. Remember we talked about microstates last class, and we said, okay, well, the molecules move around. We have different microstates. Well, if there's no movement at all, you've only got one microstate. What's the natural logarithm of 1? Take your calculator right now and take the natural logarithm of 1. You get 0. So that means that at absolute 0, there is no entropy. Entropy is 0. And so that is what we use as our reference point. So the next slide is all the same, except I just added this to it here. I didn't have room on the last one. So how do we get the difference in entropy? The difference in entropy of a perfect crystal, so at 0 Kelvin, and the substance in its standard state is S naught. Okay, that's what S naught is. And then where do we get the S naught values? In our textbook, the OpenStax textbook, you get the S naught values, and naught just means the standard state. You get them from Appendix G, and these are the standard entropy values. And so if you want to calculate the standard entropy of a reaction, here's the formula right here. And you probably recognize this formula or something close to it, because this formula is very close to the formula that you used in General Chemistry 1 to calculate the change in enthalpy of a reaction. And that is that the change in entropy of the reaction is equal to the sum of the entropies of the products multiplied by their stoichiometric coefficients, subtract the sum of the standard entropies of the reactants multiplied by their stoichiometric coefficients. So again, very similar to the equation that we use to calculate delta H, or changes in enthalpy, in General Chemistry 1. Well, let's talk about these standard entropies for a second here, right? I said, you know, oops, what's going on here with my computer? Just give me a sec. Yep, okay. The S values. Okay, these are standard entropy values. Let's talk about these for a second. What does it mean by a standard value? Well, these standard entropy values that you would find in Appendix G, okay? Sorry, I'm having a problem with my computer, you guys. Just give me a second here. Oh, shoot. What's going on? Sorry. Sorry, I'm having like a serious problem with my Teams right now. Shoot. Just give me a second here. Okay, I won't be able to type in the chat, and I'm having a problem with my Teams. But can you guys still hear me? Because I can still see my Teams. It's just I'm having a problem on my MacBook. Can you guys still hear me? Okay, good. All right, well, let's just continue. Sorry about that. I'm having a serious problem with my MacBook. Anyhow, I don't think it's going to affect the remainder of the lecture. If it conks out or something, we'll solve that problem when we get there. Anyhow, so standard entropies are entropies for 1 mole of a pure substance at a pressure of 1 bar. 1 bar is pretty much the same as 1 atmosphere. They're very close. So sometimes you'll see me say 1 atmosphere. Sometimes you'll see me say 1 bar. In fact, our book even refers to that. A temperature of 298 Kelvin. If you've got a solution, it's a 1 molar solution. And of course, we can use these standard entropy values to calculate the delta S naught for a process, and we use the values that are in delta G. Here are some standard entropy values. You know, this is the kind of slide you could kind of sit here and park on it for a while. I'll try not to take up too much time on it right now, but I want to show you a couple things. It says here, standard entropies. This is at the bottom. That's where I'm looking. So standard entropies selected for some substances at 1 atmosphere. So again, that's close enough to 1 bar and 298 Kelvin. So you even see here, it says approximately equal to 1 bar. But what I find really interesting about this is, remember where we started this lecture, where we ended the last lecture, was talking about factors that affect entropy. You can see that exemplified in this table, okay, pretty easily. For example, here we have some carbon-containing compounds. If you go from, so this is, if you go from methane to ethylene to ethane, you notice that you still have all these molecules in the gaseous phase. They all contain just carbon and hydrogen, but what's happening? The number of carbon and hydrogen atoms is increasing. Okay, what's happening to the entropies? All right, they're increasing. Another simple example, you go from carbon monoxide to carbon dioxide. What do you see? The entropy increases as you increase the number of atoms in the molecule. Same thing here. This is the first molecule here. This is methanol. This is ethanol. Ethanol just has more carbons and more hydrogen, so you see that entropy increases. Look at, here's another good one. If you go from water in the liquid phase to water vapor, right? The gas should have more entropy. Yeah, makes sense. Like, you can see a whole bunch of good examples here. Look at this one. You go from H, right? Just a hydrogen atom in the gaseous phase. Maybe I should use a different color. But you go from a hydrogen atom in the gas phase to a hydrogen molecule. More atoms, more mass, right? The entropy increases. So that's kind of cool. Also, you see an example of allotropes, right? Graphite and diamond. We talked about how the transition of diamonds to dust is actually a spontaneous reaction, isn't it, right? It's slow. It's immeasurably slow at room temperature, but it is spontaneous. And so you can see the relative entropies of graphite and diamond here. Anyhow, kind of interesting. What else? This is me just rehashing a concept that we looked at, 2 slides ago, which is the formula for delta S. I don't think I could help myself. I just wanted to show you that it's the exact same, or pretty much the same reaction that you saw for calculating delta H. Do you guys remember that formula from General Chemistry 1? How to calculate the change in enthalpy of a reaction? I hope so. Does this formula look familiar to anybody? Please say yes. See, I might not be able to see what you guys are typing now. Oh yeah, okay, cool. I can see what you're typing. Yeah, okay, well this is an important reaction. And remember that the final exam for General Chemistry 2 covers General Chemistry 1 and General Chemistry 2. So it's a very important reaction in chemistry. All right, so there we go. So this is the formula that we would use to calculate the change in entropy of a reaction. Well, with all that in mind, let's get into some practice problems here. Practice problem number 2. Again, I have the solution to this one posted to Canvas. Very simple problem. I don't like to use the word simple in chemistry class, but I think this one is pretty doable for most of my students. It just says, using the standard entropy values that are shown here. So anything that's a gas would be 1 atmosphere. Anything that's a liquid would be a 1 molar solution, room temperature. It says calculate the delta S of reaction. So sort of a shortened version of that formula is that delta S naught of a reaction is going to be equal to the sum of the stoichiometric coefficients of the standard enthalpies of the products, subtract the sum of the stoichiometric coefficients multiplied by the standard entropies of the reactants, like that. So that's the formula that we're going to use. So the delta S of our reaction is going to be equal to the standard enthalpy of H2O in the gaseous phase, subtract the standard enthalpy of hydrogen in the gas phase plus 1/2 times the standard enthalpy of oxygen in the gaseous phase, like that. Oops, I meant to add these two together. There we go. Now keep in mind, I put the 1/2 here because we only have 1/2 mole, right? The standard enthalpy of oxygen that's given here is for 1 mole. So we only have 1/2, so we're going to multiply that by 1/2. Now we just have to plug some numbers into our equation. So we have, oops, where's my black pen? Come on. There we go. So we have, son of a gun. There we go. We have, let's see, 189, right? So we have 189 joules per mole Kelvin, right? That is the standard enthalpy for my water in the gaseous phase. I'm going to subtract the sum of the standard enthalpy of hydrogen in the gaseous phase, which is 130.6. So 130.6 joules per mole Kelvin. Notice that the units are not joules per mole, it's joules per mole Kelvin, plus 1/2 multiplied by the standard enthalpy of oxygen, which is 205. So 1/2 times 205 joules per mole Kelvin, like that. So we get that our delta S naught of reaction is going to be equal to 189 joules per mole Kelvin. Subtract, and I simplify this to 233.1 joules per mole Kelvin. I know I have an extra sig fig in there, whatever. And then delta S of my reaction is going to be equal to negative 44 joules per mole Kelvin, like that. And we see that entropy is decreasing because my delta S is a negative number. Does that make sense based on what we talked about a few minutes ago? Right here, we're starting out with 1.5 moles of gas, and we're ending up with 1 mole of gas. So yeah, it makes sense. The entropy should be decreasing. All right, there we go. All right, let's move on from there. And let's take a look at question number 3. Give me 1 second, you guys. I'm having a problem with my computer. Jamil, just to address your question while I'm fixing my computer here. No, the standard entropy of oxygen and hydrogen is not going to be 0, right? They're going to have disorder, right? They're gases at room temperature and 1 atmosphere of pressure, so there's definitely going to be disorder associated with those. You might be getting those mixed up with the heat of formation of an element in a standard state. Could that be it? Right, the heat of formation. Yeah, okay, good. Yeah, the heat of formation of oxygen or hydrogen would be 0, okay, but not the enthalpy, not the standard enthalpy. All right. So, and then you'd see that standard free energy would also be 0, but not entropy. Okay, let's move on to question 3. Sorry, I'm having some technical difficulties here with my computer, which I'm trying to work through here. Anyhow, let's keep going. All right, question number 3 says, take a look at this reaction and figure it out. It says, using the following standard entropy values, find the delta S of the reaction. So if we go back to the last slide, we can just copy and paste the formula. It's the exact same formula. Come on. Let's see here. So copy the formula, and then we'll paste it over here. Come on. There we go. So there's the formula that we're going to use. Let's try it again. So we have that our delta S naught for our reaction is going to be equal to the standard entropy of my HCl, which is 187 joules per mole Kelvin, subtract the sum of 1/2 times the standard entropy of hydrogen, 130.6 joules per mole Kelvin, plus 1/2 times the standard entropy. Maybe I could put these in brackets. 1/2 times the standard entropy of chlorine, which is 223 joules per mole Kelvin, like that. When you punch all that spinach into your calculator, you end up simplifying this to 187, subtract 176.8 joules per mole Kelvin, and then you end up with a delta S for your reaction, which is equal to 10.2 joules per mole Kelvin, like that. So that's the delta S for this reaction. So just a little bit of practice, and so you see that entropy is increasing in this case. Okay, so we are increasing entropy, and it wouldn't be intuitive in this case, right? Because you're starting with a total of 1 mole of gas over here, and you're ending up with 1 mole. And so this is an example where it pays to do the calculation. You have to do the calculation. All right. Well, let's keep cooking here. Okay, let's move on from there, and let's talk about the entropy changes of the surroundings, right? What have we covered in the past few slides with these beautiful problems, all this concept? We were talking about the delta S of a reaction. What is a reaction? A reaction is a system, right? That's all we've been talking about the past few minutes. But we said that the second law of thermodynamics says that in order for the reaction to be spontaneous, that the change in entropy of the universe, which is equal to the sum of the change in entropy of the system and the surroundings, has to be greater than 0. All we've done is evaluated the system. What about the environment around the system? What about the surroundings? And that's what we're going to take a look at now. Not as intuitive, but I'm going to try to explain it to you the best I can so that you'll understand what the heck is going on when we look at entropy changes in the surroundings or the environment around that reaction. So delta S of surroundings. So see if you can follow along with me here. I'm going to read some of this. It says that at a constant pressure, the size or the magnitude of the change in entropy, the change in disorder of the environment around the reaction, the delta S of surroundings, depends on what? It depends on the amount of heat that's absorbed or lost by the surroundings, as well as the temperature of the surroundings. So this is a key equation right here. that the delta S of the surroundings is equal to the negative delta H of the system. So divided by T. So that's the negative of the enthalpy of the system divided by the temperature. Okay? So and this is a really key equation. Okay? Now let's examine this equation in some detail here. You probably notice that the change in entropy of the surroundings, right, the environment around the reaction, is going to have the opposite sign of the enthalpy of the reaction, right? Because system is the reaction. Well, does that make sense? Yeah. Yeah, I think it makes sense that they have opposite signs. Why? Because if you have a system, a reaction that is losing heat, so this would be an exothermic reaction, right? Then the heat, right, that's going to flow into the surroundings, and it's going to cause those particles to move faster, right? They're going to have more kinetic energy, and therefore entropy increases, right? Give me a thumbs up if that makes sense to you. If you have an exothermic reaction, exothermic system, heat is going to flow out into the surroundings. Those particles are going to move faster, and therefore their entropy is going to increase. Good. I'm glad you follow me on that, because you'll understand the next point. What if you have an endothermic reaction? It's going to be the opposite. Endothermic reaction. That's going to cause an entropy decrease in the environment. Why? Because it's taking heat from the environment or the surroundings, and therefore those particles are going to move slower, right? So we see that the delta S of our surroundings is directly proportional to the negative of the delta H of the reaction. So it's going to have an opposite sign of the enthalpy of the reaction or the system. Well, what about the delta S of surroundings with respect to that temperature? Well, you notice that it's the change in entropy of the surroundings is inversely proportional to temperature. Why would that be? Okay, well, temperature, as you know, we spent a lot of time talking about temperature in Gen Chem 1, a little bit of time talking about temperature in Gen Chem 2. But the temperature, which is a measure of thermal energy of the surroundings, is directly related to its entropy. Now, you might get confused and say, well, no, they're inversely related here. And then you said they're directly related here. Hold on. Here I'm talking about a change in entropy, and here I'm talking about just the entropy of the environment around the reaction before the reaction occurs. Okay, so if the temperature of the environment is high, right, the environment surrounding the reaction, if the temperature is high before you start the reaction, that means the molecules in the surroundings are already moving super quickly to begin with. So after the reaction occurs and there's a change in enthalpy, if this is already really high, that means that this is going to have, it's going to have, if the temperature is high, then the entropy is already high. Sorry, I shouldn't have related it to this equation. But the idea is that the entropy of the surroundings is already high if the temperature is already high. The converse is true, right? If the temperature of the surroundings is low, then the entropy of the surroundings is low. So what does this all mean? It means that when the reaction absorbs or releases heat, the change in thermal energy, the change in temperature of the surroundings, it changes the thermal energy and the temperature of the surroundings, therefore its entropy. So if we think about this equation here, okay, if the temperature is already high, right, if that's already a really big number, think if this number is really jacked up, okay, if this is, the T is, the denominator is huge, right, then this is going to be it's going to divide this number by a big number, and therefore you're going to end up with a small change in entropy. Okay, so all that means is when you start out, if your temperature of your surroundings is already high, you're going to have a smaller change in entropy than if the temperature around the environment was low, right? If this was a really low number, right, something really small, well then the change in enthalpy is going to be big, okay, compared to, right? And therefore you're going to have a big change in the entropy of the surroundings. All right, so those two factors are important, okay? Factor number one, that the delta H and delta S have opposite signs, and then the fact that delta S of the surroundings, the change in entropy of the surroundings, is inversely proportional to the temperature. Okay, there we go. So how do we put all this together? Well, what's great about this formula that we just saw on the last slide, okay, is that now we can take our second law of thermodynamics, right? We said that when the change in the universe, change in entropy of the universe, which is equal to the change in entropy of the system, plus the change in entropy of the surroundings, we said that when this is greater than 0, the reaction is spontaneous. Well, hold the phone. Why don't I just take this equation and plug it in here? Because it would be really annoying to try to have to measure everything in the surroundings, right? Now I can make a new equation, this one here, where I have everything described in terms of the system. Look, I have the entropy of the system here, and I have the enthalpy of the system. So that means all I have to be concerned about is the reaction, nothing more than the reaction. So this is just the second law of thermodynamics written another way, right? That the delta S of the universe is equal to the change in entropy of the reaction minus the change in enthalpy of the reaction divided by the temperature. When that is greater than 0, I have a spontaneous reaction. Okay? And if you're wondering, what the hell's the point of all this? Like, I'm not following you 100%. The whole point is this. Let me erase everything so it doesn't confuse you. Here I had system and surroundings. Because of this formula, now I have just the system. The system is the reaction. Okay? It would be really annoying to try to have to measure, stick thermometers in your environment and try to figure all that kind of stuff out. So now we have everything defined in terms of the reaction only. All right, that's a beautiful thing. Well, with that in mind, let's take a look at a practice problem and see if we can calculate some delta S's here. I'll try to walk you through this one. Question number 4, let me make sure. No, I don't have enough space probably to solve the whole thing. Let's see. It says, take a look at this reaction. So this is actually a physical process going from water in the liquid phase to water in the gaseous phase. So this is a vaporization. And it says calculate delta S of the system, which is the same thing as delta S of the, right? This is delta S of the reaction. And we have some delta S values right here. Well, let's do it. So we have our system, which is going to be our reaction. So for A, we'll put the delta S of our reaction. And again, this is standard state. That's what all these knots mean. And if you're like, what is knot? Knot is all this. This is a knot. And you're like, not like K-N-O-T? No, not like N-A-U-G-H-T. Okay, there we go. It is not for knot that I taught you about knot. Okay, and not knots. All right, anyhow, there we go. So delta S of the reaction is going to be the sum of the stoichiometric coefficients of the entropy multiplied by the entropy of the products, subtract the sum of the stoichiometric coefficients multiplied by the entropy of the reactants, which is the same thing as saying the entropy of the water in the gaseous phase or the steam, subtract the standard entropy of the water, son of a gun, of the water in the liquid phase. Okay, so we get that our delta S for this reaction is equal to 187.7 subtract 69.9 joules per mole Kelvin. We'll put all that in there. And we end up with 117.8 joules per mole Kelvin. So you see that the change in entropy for the system, for the reaction, is positive, right? That's just for our reaction. Does that make sense? I'd say, yeah, it does make sense. Why? Because I'm going from a liquid to a gas. So I should have a change in entropy for the, or positive change in entropy for the reaction. Let's take a look at B. It says, evaluate the standard change in entropy for the surroundings at this temperature. Well, we saw that the standard entropy change in the surroundings is equal to the negative of the delta H of the reaction divided by the temperature. And they've given us the delta H for this reaction. So we have 40.7 kilojoules per mole. So we'll say negative 40.7 kilojoules per mole divided by the temperature, 298 Kelvin, given to us, 298 Kelvin. We divide that and we end up with negative 0.13 0.37 kilojoules per mole. Or you could write this out in joules per mole Kelvin. I'm just going to multiply that number by 1,000 because I know that in 1 kilojoule, there are 1,000 joules. So I could write this out as negative 137 joules per mole Kelvin. Notice that entropy is usually in units of joules per mole Kelvin, and enthalpy in Gibbs free energy, which we're going to look at later if you read the textbook, is given in kilojoules per mole. Okay, and this is usually, you can see that I put the answers here in kilojoules per mole Kelvin. I don't know why I did that. Anyhow, there we go. So you got that, and then next it's asking us to calculate the delta S naught of the universe. Okay, which is going to be equal to the delta S naught of the reaction minus the delta H of the reaction over T, right? And it's not minus, but it's plus the minus this, right? So there we go. So we plug in our numbers. We have 117.8 joules per mole Kelvin. Subtract 137 joules per mole Kelvin, and we end up with negative 19 joules per mole Kelvin, like that. That's our delta S of the universe. Negative 19 per joules per mole Kelvin. So I have a question for you. Is this a spontaneous reaction at 298 Kelvin, yes or no? Yeah, definitely not. No. No, because delta S of the universe is negative, right? And in order for a reaction to be spontaneous, based off of the second law of thermodynamics, when the reaction is spontaneous, the delta S is going to be greater than 0. Okay, and since it was less than 0, it's going to be a non-spontaneous reaction. Okay, so you've got to be fully aware of the second law of thermodynamics in this class, okay, which we can use to predict spontaneity. Now, again, I told you that it's really annoying to try to measure the entropy of the surroundings. And I told you that the change in entropy of the surroundings is equal to the negative delta H of the reaction divided by the temperature. And we're going to use that to develop a new equation for a new variable that's called Gibbs free energy. Let me show you how you're going to do that. I have the derivation shown on this next slide. So if we have our second law of thermodynamics, we know that the change in entropy of the universe, which is equal to the change in entropy of the system plus the change in entropy of the surroundings, when that is greater than 0, we have a spontaneous process, don't we? Absolutely. I also told you that this variable is equal to negative delta H of the system over T. So let's plug that in. This equation we just saw, we just wrote it in the last problem, didn't we? Okay, now what if we take that whole equation and we multiply the whole thing, we multiply the entire equation by negative T. Then we end up with this expression right here. Negative T delta S of the universe is equal to delta H of the system, so the change in enthalpy of the system, subtract T times the change in entropy of the system. And we define this negative T delta S as being a new variable that we're going to call delta G, which is called Gibbs free energy. So when we see delta G, it means Gibbs free energy change, right? Change is represented by a capital D in the Greek alphabet, a delta. So here's our new formula. The delta G, change in Gibbs free energy, is equal to the delta H of the system minus T times the delta S of the system, or written another way, and if you've read the book, you've seen this formula many times, which is delta G is equal to delta H minus T delta S. You're going to see this formula come up over and over and over in this class. Now, about the sign of delta G. If the delta S of the universe is a positive number and we have a spontaneous reaction, Well, we're multiplying that delta S by negative T. So that would mean that when I have a negative delta G, I'm going to have a spontaneous process, won't I? Right? So you need to be fully aware of the fact that when you have a negative delta G, when delta G is less than 0, you have a spontaneous reaction. When delta G is greater than 0, you have a non-spontaneous reaction. And delta G, when it's equal to 0, that's when we have a system equilibrium. Right? Again, the reason that the sign is changed is because delta G is equal to negative T multiplied by the delta S of the universe. Give me a thumbs up if you follow me on that concept, because we're going to use it a lot. Okay, cool. All right. Even though I'm having a problem with my Teams, I can still see what you're typing. Okay. All right. So you might be wondering, what exactly is Gibbs free energy change? Well, the book goes into a very short treatment of what Gibbs free energy is, and I encourage you to read that. But Gibbs free energy change is simply the free energy that's available after a reaction has been completed, that's available to do work. Now that treatment is kind of beyond the scope of our textbook. However, we're just going to use it to predict the spontaneity and it allows of a reaction, and it allows us to do it by focusing on the system only, which is just our chemical reaction. So we don't even have to worry about the environment. Well, take a deep breath. That's a lot of information. A lot of information that I've just told you, okay? A lot of interesting information, but a lot of information nonetheless. But if you think about really, what does it boil down to? What have we mostly talked about today? We talked about changes in entropy, and we talked about the second law of thermodynamics. We talked about where standard entropy values come from. We talked about absolute zero, okay? And that when we have a substance at absolute zero, the standard entropy would be 0. And that's really the crux of it, okay? Because this formula that I have in the green box, the formula for Gibbs change of Gibbs free energy, is nothing more than a rewrite of the second law of thermodynamics, isn't it? Really, it's all it is. It's just a rewrite of that formula. So now what we're going to do is we're going to do an examination of this formula that I have in the green box, but we're going to take a look at it from the point of view of changes in enthalpy, delta H, and the changes in entropy, delta S, in our reactions. Right? Everybody who's hearing the sound of my voice should know how to calculate the change in enthalpy for a reaction. We did that in Gen Chem 1. That was in the thermochemistry chapter. And we've looked at how to calculate the change in entropy. We've discussed a lot about what entropy is, haven't we? So now we're going to take these two concepts, enthalpy and entropy, and we're going to take a look at what would happen if I had an endothermic reaction or an exothermic reaction. What would happen if I had an increase in entropy or a decrease in entropy? What's going to happen to my delta G in those kinds of situations? Well, it says here that a spontaneous reaction, one with a negative delta G, usually, now generally speaking, right? Generally doesn't mean, when I say the word generally, that doesn't mean all the time, does it? It means a lot of the time are going to be exothermic reactions, right? Because if delta G is going to be negative, it helps for you to have a negative number here, doesn't it? Right? If the reaction releases heat, we're oftentimes going to have a spontaneous process, okay? A negative delta H is going to contribute to a negative delta G. We went over this quite a bit last class. Remember I had a picture of the Hindenburg? I said, oh, you're releasing all this heat. Is it spontaneous? And you guys were like, hell yeah, that's a very spontaneous reaction. But remember, we also looked at exceptions, didn't we? You can hear me banging on my desk, right? We looked at exceptions. We looked at when we convert ice into water at room temperature. That's an endothermic reaction, but it's spontaneous, isn't it? Okay, so generally speaking, when we have an exothermic reaction, we're going to have a spontaneous process, but that's not true all the time, is it? Okay, so what if we evaluate delta S? Well, generally speaking, if delta S is increasing, right, if it's positive, that's also going to contribute to a negative delta G. If you're like, what do you mean by contribute to, Mr. Dion? Look, let me prove it to you. I'm going to prove this to you right here. If your delta G is equal to delta H subtract T delta S, if you have a negative delta H. You've got a negative number, and you're subtracting your T. T is always positive, right? That's an absolute temperature. There's no negative Kelvin. It doesn't exist. It stops at 0. So we're going to leave that out. Now, if your delta S is a positive number, then you've got a negative subtract the positive. If you take a negative number like -2 and you subtract 1, what do you get? You get -3. So that means when you have an exothermic reaction and an increase in entropy, you're going to get you're going to end up with a delta G that is always negative, right? So it's always spontaneous. Always spontaneous. I don't know if I have this written down in my slides or not. I probably do, but anyhow, give me a thumbs up if you follow me on that idea, because now we're going to take a look at what if we flip the signs of these. Cha? Okay, thanks, Katie. All right, I'll take it. Good. Okay, because now what we're going to do is we're going to extrapolate this idea into, well, what if you had a positive delta H and a negative delta S, right? You know, we have to look at all the different scenarios, okay? So notice that the value of the T delta S is going to depend on temperature too. So let's take a look at all the possible scenarios. We'll do that in a second. Okay, this is just a little bit of rehashing and just one more concept before we take a look at a problem, which I think I have, next, which is going to deal with all the possible scenarios. We'll probably finish up the lecture somewhere around there. Anyhow, again, temperature is always positive. So the sign of delta G tells us whether the reaction is spontaneous or not. I mean, you got to have this memorized, you guys. You've got to know this, that when delta G is positive, you have a non-spontaneous process. When it's negative, you get a spontaneous process. And when it's 0, you're at equilibrium. Simple as that, right? Because remember, you know, when we tie these two things together, and am I repeating myself? Heck yeah, okay? We said that this is equal to negative T delta S, so that's why their signs are opposite, okay? So I think we've established that. Now, what about at equilibrium? What if we wanted to find the temperature at which a process is at equilibrium? Well, if it's at equilibrium, my delta G is equal to 0. I can just rearrange the formula. 0 is equal to delta H minus T delta S. I can solve for T, and that's just going to be delta H over delta S, right? That makes sense because the units of delta H are kilojoules per mole. And if I divide that by kilojoules per mole Kelvin, right, you see that these are going to cancel, and I'm going to end up with the units of Kelvin. All right, and if you're wondering, oh, okay, cool, when do I have to use that, Mr. Dion? Of course. And am I going to go over an example with you? Of course, okay? I'm not just going to throw it out there on a test like, hey, I never showed you this, but here you go. Well, let's take a look at the signs of delta H and delta S and see if we can determine the spontaneity of a reaction. But before we do that, I want to take a look at this little note up at the top, okay? You can find all kinds of information about the temperature dependence of delta H and delta S. Now, do delta H and delta S depend on temperature? The answer is yeah, they do. But it's a very small dependence for little temperature changes or moderate temperature changes that we're going to take a look at in this class. And so you don't have to change or evaluate a new delta H or a new delta S at different temperatures, okay? If you're given H values at 298 Kelvin, you can just use those all the time in this class. The same thing with entropy values, okay? All right, well, let's take a look and see if we can predict delta G for all of these different scenarios. So it says here, let me write out the formula in case you've forgotten it, which is delta G, which is equal to delta H minus T delta S. So I'm going to go through these kind of slowly and see if you can follow along here. So it says if delta H is greater than 0 and delta S is less than 0, then you'd have delta G being equal to a positive number, subtract T, which is always positive, right? T is always positive, so I'm just going to leave that out. Subtract a negative number. What happens when you take a positive and you subtract a negative? Take 2 and subtract -2. What do you get? 4. So that means it's going to be always positive. Okay? So that means the reaction is going to be never spontaneous. Okay? This reaction will never be spontaneous. Give me a thumbs up if you follow me on that idea. Anybody with me on that? Yeah. Okay, thanks, Joey. I appreciate that. Good, good. All right, good. Thanks, Kelton, Allison. Great, gang. Awesome. Awesome. Well, let's try the next one. Okay, if delta H is less than 0 and delta S is greater than 0, wow, we already looked at this one, didn't we? So delta G would be equal to a negative number, subtract a positive number, which means it's going to be always negative. So this is going to be always cheapers. I'm tired. Always spontaneous. Okay, always spontaneous. There we go. You can imagine the next ones are going to be a little more interesting, aren't they? The next one is if you have a delta H greater than 0 and a delta S greater than 0. So let's see, that means you'd have delta G is equal to a positive number, subtract a positive number. So that means it's going to be affected by the delta T, isn't it, right? Or sorry, not delta T, it's going to be affected by T. You're going to have T times a positive number. So what does that mean? That means that if the temperature is really high, let's think about this. If the temperature is jacked up super high, then this term is going to be really big, and it's going to be bigger than this term, and it's going to create a negative delta G. So that means that this reaction would be spontaneous at a high temperature. So spontaneous at high temperature. And you can probably see where we're going with this. The last one is when you have a delta G is equal to a negative number, subtract your T, which is always positive, times a negative number. Okay? Well, if you're subtracting a negative, it's like adding something to it. So that means that if the temperature is really low, then this will just be a small number, and then this is going to stay negative overall. So that means that delta G is going to be spontaneous at low temperature. Give me a thumbs up if you follow me on those 4 scenarios. The 4 scenarios. All right. Good. Well, as you can imagine, let's just take a break, okay? You guys are General Chemistry 2 students. Don't you deserve a break in lecture? Of course you do. Take a little break here and just kind of discuss this for a second. You can see how easy it is for your instructor or any person in the world who writes standardized tests to provide or to give you multiple choice questions that cover this concept, okay? These 4 scenarios, okay? You have got to be perfectly aware of these 4 scenarios, which are summarized right here. So Stephen, if you need a review, it's right here, okay? If you have a delta H that's greater than 0 and a delta S that's greater than 0, like I said, the reaction is going to be spontaneous at a high temperature. If you have a delta H that's greater than 0 and a delta S that's less than 0, it's never going to be spontaneous, not spontaneous at any temperature. If you have an exothermic reaction with an increase in entropy, reaction is always spontaneous. And when you have an exothermic reaction with a decrease in entropy, it's going to be spontaneous at low temperature. Okay, so those are the 4 possibilities, all based on this formula. The delta G is equal to delta H minus T delta S. All right, there we go. So those are the 4 possibilities. Well, let's talk a little bit more about Gibbs free energy before we end the lecture today, I want to take a look at one or two problems that deal with Gibbs free energy. And then I think that on Monday, we'll spend some more time talking about Gibbs free energy. So just a little bit more about that Gibbs free energy. If we evaluate a standard free energy change, when we evaluate a standard free energy change, it says, although the Gibbs free energy change is, the equation is valid under all conditions, we're most often going to apply a standard condition. So we're usually going to be evaluating delta G naught, right? Standard conditions are going to be 1 atmosphere for a gas, 1 molar for a solution. You know, if you're a pure liquid or a solid, if you have a solid or a liquid. So under standard conditions, we can rewrite the formula to be delta G, the change in Gibbs free energy. The standard free energy change is equal to the standard change in enthalpy subtract the temperature multiplied by the standard entropy change. Again, notice the difference in joules and kilojoules. This is something I hate to see my students mix up. That kilojoules are usually used for delta G and delta H, and joules are usually used for changes in entropy because they're smaller. Okay, how do we calculate the standard free energy change for a reaction? Well, I got some good news for you. If you understood how to calculate the change in enthalpy and change in entropy for a reaction, it's the exact same formula for calculating the standard free energy change for a reaction. We take the sum of the stoichiometric coefficients of the standard free energies of the products, and we subtract that from the sum of the standard free energies of the reactants. And these can be looked up in Appendix G. If you go to Appendix G in Jamil, you'd probably notice that if you look up the standard free energy of a compound in its standard state, like say, for example, you look at Cl2 gas, right, it would be 0. Right? Its delta H is 0, but its entropy won't be 0, will it? Okay, so just something to be aware of there. So again, the formula, this only works for calculating the standard free energy change of a reaction at the temperature for which the standard free energy values are tabulated, which in our textbook is 298 Kelvin. And like I was saying to Jamil and everybody else, that when you have the standard enthalpy of formation of an element in its most stable form at standard conditions, it's 0. So I have my table open right now on my other screen, and I see that chromium 0, right? It has delta G naught F. It's right. It's 0, right? Because chromium is a solid at room temperature, right? And you could say that for any element in its standard state, right? Same thing if you had chlorine gas, you know, if you had hydrogen gas, if you had whatever, okay? So there we go. Standard states, again, the delta G of formation for elements in their standard form or their most stable form, their most stable allotropic form would be 0. Standard states for a gas is 1 atmosphere. Standard state for a solution is 1 molar. If you have a solid or a liquid, it's just a pure sample like that. All right, we got what, 2 hours left? Let's see if we can solve a couple of problems, and then maybe we'll call it a day. This one kind of came out kind of weird. The delta G's are actually here. These are the delta S values, and this is the delta H. Anyhow, whatever. First question is, does delta G depend on pressure? That might not be an abundantly clear, or the answer, I should say, might not be abundantly clear to you guys. So I wanted to go over this with you. Delta G is equal to delta H minus T delta S. Well, delta H isn't affected by pressure, and neither is T. But we saw how delta S is affected by pressure, right? Delta S is affected by pressure. So the answer is, if this is affected by pressure, okay, then the answer is yes, delta G is affected by pressure, right? Remember at the end of the last lecture, we talked about a scenario where we had some gas particles and then we had a piston like this. Let's say we had 1, 2, 3, 4, 5 gas particles. Well, if I take those same gas particles and I put them under higher pressure, 1, 2, 3, 4, 5, now they don't have as many microstates, do they? Right? There's not going to be as much room for them to move around. And so I end up with a decrease in entropy. So since Entropy is affected by pressure. Yes, delta G is affected by pressure. Okay, that's a question I had for my students. I think the first time I ever taught this class years ago. And so I thought it was a good question to something just good to address with my students. So let's take a look at question number 7. Again, these came out kind of cockamamie. These are the delta G values here. These are the delta S values here. And these are the delta H values there, okay? Anyhow, it just says calculate delta G at 298 Kelvin. So I saw that the delta G of my reaction at standard state is going to be equal to the sum of the stoichiometric coefficients multiplied the change in the standard free energy of the products minus the sum of the stoichiometric coefficients multiplied by the change in standard free energy of the reactants, like that. I'm given all my delta G values. Here's the equation. It's methane plus 2 moles of oxygen gives us carbon dioxide and 2 moles of water. So these are our products. These are our reactants. So let's start. For our products, we have carbon dioxide. Here's its standard free energy. So we have negative 394.4 kilojoules per mole plus 2 moles of oxygen. Oxygen is 0, so we can just leave that out. So we have negative 394.4 kilojoules per mole. Subtract the sum of the standard free energies of the products multiplied by their stoichiometric coefficients. I have carbon dioxide, which has a standard free energy of negative, did I put the wrong one in there? No, sorry, methane, which is negative 50.8 kilojoules per mole. I keep writing joules, don't I? Plus, shit, am I getting tired or what? Son of a gun, Mr. Dion. Okay, let's start over. So I've got my carbon dioxide plus I've got 2 moles of water, don't I? Here we go. So plus 2 times the negative 273.2 kilojoules per mole. Okay, and then I subtract my reactants, which I only have to be concerned with the methane because oxygen has a delta G of 0. So subtract negative 50.8 kilojoules per mole. All right, when you punch all that spinach into your calculator, you get that your delta G at standard state for your reaction is going to be equal to negative 890.0 kilojoules per mole. All right. Next, we're asked to calculate the delta G at 500 Kelvin. Now again, I told you that you can assume that delta S naught and delta H naught are constant with the change in temperature. So we can still use these delta S and delta H values. Yes, go ahead.
I think you messed up on H2O. It's 237.2, not 273.2.
Okay. Yeah, 237. All right, there we go.